In this video, I want to talk about the Cauchy-Riemann equations, which are a set of equations which relate partial derivatives of a function from one variable to another. What I want to do first is I want to remind you that if f is a function, so let's say you have a function f which maps some set g to the complex region C, then the derivative at some point in z naught, where z naught is in g, is defined as the limit as z approaches z naught of f of z minus f of z naught all over z minus z naught. In order for the limit to make sense, z naught has to be an accumulation point of g. So notice that in order for this limit to make sense, z naught has to be an accumulation point of the set g, but this is stuff that we've talked about in ideas that we've talked about anyway. So this is the derivative of a function at a point z naught, and this is what I mean when I say complex differentiability is this this limit. And so the other idea that I want to mention is, if you remember in the beginning of the book, we had this kind of one-to-one correspondence between, say, a point x, y in the plane and the complex number x plus iy. So if you wanted to think about the set of complex numbers, you can think of a two-dimensional plane, and then each point represents a unique complex number. And so here we can think of functions with complex entries as functions with two variables. So you could think of kind of the partial derivative is going to come naturally when you have a function which has an input with two variables in it. And in that light, let's define actually the partial derivative of f with respect to x at a point in z naught. And so what this means is that if you're going to take the derivative of f with respect to x, you're going to pretend that y's are constants. And this is going to be defined as the limit as, let's not do h's, let's do the limit as x approaches x naught, f of x plus iy naught minus f of x naught plus iy naught all over x minus x naught. Here I'm thinking of, so z naught is x naught plus iy naught. Okay, and so that's the partial derivative of f with respect to x at z naught. And likewise, we could define the partial derivative of f with respect to y at z naught. And this is going to be the same idea, except we're going to let y approach y naught. This is going to be f of x naught plus iy. So we're thinking of the x terms as being constant. And then we're going to divide by y minus y naught. So these are the partial derivatives of f with respect to x. That's what they mean. Now, what the Cauchy-Riemann equations do is they tell you that there's a relationship between these two. Okay, so the Cauchy-Riemann equations tell you that if f prime of z naught exists, okay, so if f prime of z naught exists, and I guess I should say, I need a few other criteria here, but if f prime of z naught exists on an open set G, then it turns out that the relationship between the partial of f with respect to x and the partial of f with respect to y is that the partial of f with respect to x is at z naught is equal to 1 over I times the partial of f with respect to y. And remember that 1 over I, instead of writing 1 over I, you could also write negative I, because they're the same. 1 over I and negative I are the same, but I like it as 1 over I. So this is the Cauchy-Riemann equations, and actually it goes the other way as well. If, I'm not going to write this out, it's written precisely in the book, but the point is that if this equation is true, then you know that f prime of z naught exists. Okay, so this is kind of a criteria for differentiability. The reason why these are called the Cauchy-Riemann equations, if you notice that this was plural, is that you can think of a complex function. If you think of f of z as being f of, say, x plus iy, or even f of xy, you could think of this as having a real part. So it's all the stuff without the i's, plus the imaginary part. And we'll call the real part u and the imaginary part v. Okay, and then the Cauchy-Riemann equations say, well, the derivative of f with respect to x is going to be the partial derivative of u with respect to x plus I times the partial of v with respect to x. And the partial of f with respect to y is going to be the partial of u with respect to, that's a terrible u, partial of u with respect to y plus I times the partial of v with respect to y. And if these are equal, then what the Cauchy-Riemann equations say is that u sub x plus I v sub x is equal to 1 over I u sub y plus I v sub y. And then if you think about what this means, this tells you that u sub x is going to be equal to v sub y, and v sub x is going to be equal to negative u sub y. So this is why we call them the Cauchy-Riemann equations, is that there's actually two if you think about comparing the real and the imaginary parts. Okay, and I'm cheating slightly. Really, all of the quantities that I should have had here are at the point z naught, at z naught, and so on. I'm not going to go back and fill it in too late, but this is the idea. These are the Cauchy-Riemann equations. So at this point, let's do an example and let's see how this works. And I think that once we see how it works, then hopefully everything will just kind of snap into place. So let's do that. And let's look at the function. So let's look at f of z equals z squared. And if you write z as x plus iy, you can think of this as a function of two variables, f of xy, and that's x squared minus y squared plus I times 2xy. And it turns out that f of z equals z squared is an entire function. It's differentiable at every value in the complex plane. And in particular, let's look at the partial of f with respect to x. So that's going to be the partial of u with respect to x plus I times the partial of v with respect to x. So this is going to end up being 2x plus I times 2y. And the partial of f with respect to y is going to be negative 2y plus I times 2x. And you can check that if you take the partial of f with respect to x, it's going to be 1 over I, or negative I, times the partial of f with respect to y. And this is going to be true for all points z naught in the complex plane. Okay, so you can check that those are going to be equal for all values. Okay, so that tells you that f of z equals z naught is differentiable everywhere, since this equation is true everywhere. So that's the Cauchy-Riemann equation.